Okay guys, we're continuing on chapter 2 and we're starting with the photoelectric effect. Now the photoelectric effect is when light shined on a metal, okay, can induce a current to flow. Now the problems they were having with the photoelectric effect wasn't the fact that you could use light shined on a metal to create a current flow. It's that there were some things that didn't quite fit in with classical physics. Number one, there was a threshold frequency. Now the threshold frequency is a minimum frequency of lights that's needed to see the photoelectric effect happen. If the light is below this frequency, even if it's really bright, no photoelectric effect. If it's above this frequency, even if it's dim, you see the photoelectric effect, you see current. Classical physics would have said bright light would have gotten you a current faster than dim light, no matter what the frequency, and there wouldn't have been a threshold frequency. So that threshold frequency and the fact that once you hit it, you get a current to flow, dim light, small current, bright light, bigger current, and that you couldn't build up energy at a lower frequency and get it to start eventually was really counter classical physics. Now, Einstein was a voracious reader of scientific publications, and Einstein was aware of Planck's results and Planck's idea that the energy of an atom is quantized. Okay? So Einstein said, and Planck went one step further and he said that an atom could only absorb or emit certain quantities of energy. So Einstein was looking at that and said, what if I apply that in some way to my photoelectric effect ideas? And he said, what if energy comes in little energy packets called photons? So we have the photon, which is an energy packet. The size of the packet is frequency dependent. Okay? And the brightness of light has to do with the number of photons. Brighter light, more photons. So Einstein starting to give energy, light, a particle behavior coming in hunks. Now here's what Einstein said. Einstein said that light is made up of these particles called photons, okay, little energy packets that are frequency dependent. And when light hits the metal, the atoms in the metal interact with one photon at a time. If the photon isn't enough to remove an electron from the atom, the photon is just spit back out, bounces out of there. If the photon is of the right energy to strip the electron out of an atom, then you have current. Any photon that has more energy than the minimum to get the electron out of the atom works too, but you have to have a minimum to purchase a vehicle. It's like if you walked into a car dealership and they were selling cars for cash and cash only, and the cheapest car they had in the lot was $15,000. If you walked in with $7,000, they'd say, sorry, you don't have enough money, you got to go away. They don't say, sit in our lobby and wait till somebody walks in with $8,000 and you can purchase the car together. They send you on your way. You walk in with $35,000, they say, we got the car for you, here you go, buy the car, off you go. So you got to have the minimum energy photon to create the photoelectric effect, okay? Now, this explained everything. If they were only interacting with one photon at a time, and a photon was a specific energy size packet, once you hit the right frequency, Okay, the sheet of metal was being bombarded with photons of the right energy to knock an electron loose. Everything took off and it was going. If you're below that frequency, they just bounced away. If you had dim light, you have a low current because you have very few photons hitting the metal per unit time to create the current. Brighter light, more photons per unit time, then you got a stronger current. So everything about the photoelectric effect could be explained by this explanation of the photon. All right? Now, Einstein worked with Planck's equation, and he came up with the following equation. It says that the energy of a photon is equal to h, which is called Planck's constant, times nu, the frequency. Okay? You can also see it written this way. Energy of a photon is equal to hc over lambda, because frequency, well, speed of light equals lambda times nu, so nu would equal c divided by lambda. It's just a substitution. Okay? So if we know the frequency of the light and Planck's constant, we can figure out what the energy of a photon is. We know the energy of a photon we need. We can calculate the frequency of the light. Now we're going to look at problem 2.2 on page 83. Now, it says a 100-watt light bulb radiates energy at 100 joules per second. So we've got 100 joules per second. Joule, remember, is a unit of energy. If all of the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? So we're asked number of photons. Okay, with the wavelength of light here, I can get the energy of one photon. So my step one is going to be to calculate energy of one photon. And I'm going to use energy of a photon equals h nu. Now, when I write out Planck's constant, okay, this isn't a number I expect you to have memorized, just be able to use. It's 6.626 times 10 to the minus 34 joules times seconds. And frequency I don't have frequency, I have wavelength. So I'm going to think about this as hc over lambda. So I've got h. C is the speed of light, 3.00 times 10 to the 8 meters per second. Notice that the seconds are going to divide out. And notice that speed of light is in meters. I'm given my wavelength in nanometers. So I'm going to have to go 1 meter for every 1 times 10 to the 9 nanometers. And so it gives me 5.25 times 10 to the minus 7 meters. So if I plug that in, I get the energy of a photon, 5.25 times 10 to the minus 7 meters. So let's get the energy of a photon. So 6.626 exp 34 negative times 3 exp 8 divided by 5.25 exp 7 negative. I get the energy of a photon to be 3.79 times 10 to the minus 19 joules. Notice the meters and meters divide out. Now that's energy of a single photon. 3.79 times 10 to the minus 19 joules. And we've got 100 joules per second. So a number of photons, which is what I'm going to calculate here in step 2, is going to be 100 joules per second times 1 photon for every 3.79 times 10 to the minus 19 joules. So I'm going to take 100 and divide it by 3.79 times 10 to the minus 19. And I'm going to get 2.64 times 10 to the 20 photons per second. So notice joules and joules divide out. I'm left in photons per second. Okay? So we've got 2.64 times 10 to the 20 photons per second. Okay, so that's a simple calculation. There's more practice 2.2 on the same page. Okay? Now, I've also put the work in the notes so you can see it there. Last of the 3 phenomena that shook the foundations of classical physics and was explained, okay, using new ideas building off of Planck and Einstein, was line spectra. Now, we're going to be looking at line spectra in lab. A line spectra, atomic line spectra, these are lines of colors of light seen when light given off by excited atoms pass through a prism. Okay, they're line spectra. Okay, so in other words, you don't get a full rainbow, you get lines of color. Now I'm going to show you a chart. Okay, so let's walk around the room over here. Over by the side sink is line spectra. Okay, now this is an old chart. The colors aren't super bright, but you can see just certain lines of color. Up there is the continuous spectrum, the full rainbow. Okay, but when I excite mercury atoms, I get only certain lines of color. When I excite sodium, we only get 2 lines of yellow. Okay, so those are line spectra. Every element, it turns out, has its own unique set of lines. Okay? So the question is why? Why are there only certain lines of color for certain atoms? Line spectra couldn't be explained by classical physics. So in steps along a young scientist by the name of Niels Bohr, Niels Bohr worked in the lab of Rutherford. Okay, think about Rutherford. He was the one who found the nucleus of the atom for us. All right, so what's Niels Bohr going to do? Well, he said Planck went out with some really hairy, off-the-wall ideas. So what if I go for some really off-the-wall ideas? So Bohr decided to look at the line spectra for hydrogen. So we're going to get the Bohr model of hydrogen. A model is the same as a hypothesis. It's an educated guess on limited data. Okay? So he's basing his whole idea about line spectra off of one atom, the hydrogen atom. The reason he chose the hydrogen atom, it has one proton in its nucleus and one electron outside its nucleus. So it's the simplest atom out there. So let's talk about what Bohr said. He says there are only certain allowable energy states for electrons inside the atom. That's just building on Planck's idea that there are allowable energy states for the atom. People said, okay, we agree with that one. Now he called these energy states orbits. He said that the energy states of hydrogen are linked to orbits for electrons. Now, an orbit is a flat circular pathway. Okay? So, if we start to think about the Bohr model of the atom, I've got a nucleus there that's got one proton, and you can think about it as having these kind of racetracks, circular pathways around it. So an electron could be here and moving around this one, or it could be here moving around this one, or it could be here moving around this one. But it has to be in one of those orbits. Okay? Now, an electron can be in one of those orbits, but it can't be out in between. So an electron can't be here running around. It has to be in one of those orbits. And electrons can jump from one orbit to another. So when an atom absorbs energy, the electron jumps out. When an atom emits energy, electrons fall down. Okay? So absorb, we jump out. Come in, they emit. If I don't have enough energy to jump to another energy orbit, it just falls back down to where it was before. And if you pump it full of enough energy, what we see in the photoelectric effect is it gets stripped totally out. Okay? Now put a pretty image in your notes on some of the jumps for a hydrogen atom in the visible spectra. Okay, so you can see that this jump equates to this orbit. The first orbit, he said, was n equals 1. Second one, n equals 2. Third one, n equals 3. N is the orbit state, according to the Bohr model of the atom. Okay? And Bohr could precisely calculate where these orbitals were and what the jumps would be. So the lowest energy state for the hydrogen atom, he called it stationary state. Okay? If the electron had jumped out into a larger orbital, he called it an excited state. So stationary. Stationary state, electron in the lowest energy state. Well, lowest energy orbital. No, orbit. And if it's excited state, electron in a higher energy orbit. Now, there are a couple of things that Bohr said that were a little iffy. One, he said that when an electron was in a specific orbit, it didn't radiate energy. Okay? And that it can make these precise jumps, but it really bothers people. In classical physics, when a particle follows a circular pathway like this, it radiates energy. And we have to be able to explain why then the electron doesn't spiral into the nucleus. And Bohr couldn't explain it. He just said it's in these orbits, and the orbits are fixed, and when an electron is in there, it's stable. Okay? And the stationary state is the bottom one. Also, Bohr's model was a one-electron model. The minute they tried to apply all of Bohr's calculations and all of Bohr's ideas to the next atom up, helium, with just 2 measly little electrons, it didn't work. Okay? And so they came back to Bohr and they said, why, Bohr, would there only be certain allowable radii, certain allowable orbits for your system? What can you show us in nature that has only certain allowable states? Well, Bohr was scratching his head, trying to figure out what would give only certain allowable states. And a young Italian physicist named Louis de Broglie said, I know what gives us that kind of situation. De Broglie said, what if electrons showed some sort of wave behavior? Okay? Now, de Broglie was thinking about standing waves. It's a system in nature where there are only certain allowable states. Now, you can try this at home. Okay? You can get a string and tie it off and hold one end taut, and you can pluck it. And you'll see it vibrate. I've got a rubber band here. Let's see if I can do it with this rubber band. So if I stretch the rubber band here, okay? Stretch it. And I pluck it. You can see it vibrate, okay? If I take my slinky here and I start shaking it, I can create a pattern. If I don't shake it right, I get gobbledygook. But if I shake it just right, okay, we're used to that pattern. So I can, yeah, that's a standing wave. Okay? Now, de Broglie said, what if